All right, so we're going to continue on with section 10.2. This is part 3. So we're talking about derivatives of how to calculate derivatives of parametric curves. We're going to jump into another example. So for this one, there are two parts to this one. This one's going to be a long one. I don't want to break this up. I want to keep it in one video, so this video might be a little longer. But let's do this. We're going to find the tangent line to the cycloid x is equal to r times theta minus sine theta. So we did this, we derived this equation I think last time or the time before, and r times 1 minus cosine theta for the y coordinate at the point where theta is equal to pi over 3. Okay, so let's jump into this. So we want to find the tangent line to the cycloid. So we're going to have to compute the derivative. So we want to compute dy dx. This is going to be, so remember from our formulas last time, this is dy dt over dx dt. So if I just look up here, I can calculate dx dt and dy dt from those things. So when you're doing this, sorry, this is not t, this is theta. So let me do this, use the same notation, d theta. So when you're doing this, note that, r here is constant. So when I'm taking a derivative, I ignore it when I'm doing it with respect to theta. So when I take the derivative of the first one, I'm going to get r times 1 minus cosine theta, and dy d theta is going to be r times the derivative of negative cosine theta, which is positive sine theta. So that's what I'm going to get for that. And when I plug this in, I'm going to get dy dx is equal to r sine theta over r times 1 minus cosine theta. And I can cancel out the r's. I'm going to get sine theta over 1 minus cosine theta. Okay, so now what I want is I'm trying to figure out what is the slope of the tangent line at theta equals pi over 3. So in order to do that, I need a point and I need a slope. Right now, slope's going to be the easiest thing to find. So if I just plug in dy dx and I evaluate this at theta is equal to pi over 3, so when I do this, I'm going to get sine pi over 3 divided by 1 minus cosine pi over 3. Sine pi over 3 is square root 3 over 2. Cosine pi over 3 is a half. So this ends up being, all right, in the intermediate steps, radical 3 over 2 over 1 half. So this ends up being the square root of 3 for the slope. So I have the slope of my line. But now I need to have a point for this. And I don't have a point yet. I have, I know the value of the parameter here, theta, is equal to pi over 3, but I don't have the x and y value. So I need to ask myself, how am I going to find the x and y value for this thing? If you look up at the very top here, I'm given an equation for x in terms of theta, and I'm given an equation for y in terms of theta. That's how we're going to think about these things. This is x as a function of theta. This is r times theta minus sine theta. Y is a function of theta, and this is r times 1 minus cosine theta. So I can figure out my x and y values just by plugging in different values of theta. And specifically, I want to figure out what the x value is when theta is equal to pi over 3. So I'm going to get r times pi over 3 minus sine of pi over 3. We already did sine of pi over 3 up there. So this is r times pi over 3 minus the square root of 3 over 2. There's not much I can do about that. That doesn't simplify at all. So let's go ahead and figure out what pi over 3 is. So if I plug in pi over 3 for theta and y, I'm going to get r times 1 minus cosine pi over 3. Cosine of pi over 3 is a half. So this is r times 1 half, so this is r over 2. So now I have a point. I have the point, so I have the slope, This is going to be the square root of 3, and I have a point, and this is going to be r times pi over 3 minus radical 3 over 2, comma r over 2. So I have a point, I have a slope, I can use the point slope form. So I'm just going to use y minus y0 is equal to m times x minus x0. So y0 here is r over 2, slope is square root of 3, x minus, and then I have this ugly mess, r times pi over 3 minus the square root of 3 over 2. And so I solve this for y, and I just get y is equal to the square root of 3, x minus r pi over 3 minus the square root of 3 over 2, plus r divided by 2. And that is the equation of my tangent line there. All right, so I'm going to move on to part B, and this is the one that takes a minute in the book. If you look at the book, it just breezes right through it. But there is a lot to, explain with this. So find the points where the curve has a vertical tangent and a horizontal tangent. Okay, so what this means is, so what you have to remember is tangents, so these vertical and horizontal tangents sometimes occur. No, I can leave that. I think that's logically sound. When dy dx, dy d theta is equal to 0 and dx d theta is equal to 0. So in order to have a horizontal or vertical tangent, I need one of these to be true. They might both be true, and then I have to do a little more analysis in terms of limits. But at the very least, these have to be true. So this one right here is going to tell me when a tangent line is horizontal. This one is going to tell me when it's vertical. And again, it's not just because the case where they both happen, I have to treat it a little more specially. So let's figure out when dy d theta. So let's look back at dy d theta. So dy d theta was r sine theta. So you can look back up there, look through the notes. I should have these posted by the time you are watching this. So dy d theta is r times sine theta. If this is equal to 0, I can divide by r, and I'm going to get sine theta is equal to 0. This happens when theta is equal to, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, whatever I want, any multiple of pi, any integer multiple of pi. So this happens when theta is equal to negative 3 pi. So ... that means this keeps on going. So any, integer multiple of pi, negative 3 pi, negative 2 pi, negative pi, 0, pi, 2 pi, so on and so forth. So just any integer multiple of pi. So dx d theta, that's going to be, so we already did that, that's r times 1 minus cosine theta. If this is 0, that tells me that 1 minus cosine theta is equal to 0, which tells me cosine theta is equal to 1. Well, what values are cosine theta equal to 1? I need to be careful here. So it's not any integer multiple like it was with sine. So for example, cosine of 0 is 1, but cosine of pi is negative 1. So I have to be careful here. It's not just the, it's not any multiple of pi. It's only the even multiples of pi. So this is going to be equal to, ... So saying that this continues off to, minus infinity. So we're going to have negative 2 pi, 0, 2 pi, 4 pi, so on and so forth. So any even multiple of pi, I'll have dx d theta is equal to 0. So what you'll notice is there are values of pi, so there are values of theta, oh, wrong one, where dy d theta is equal to 0, but dx d theta is not. And those values of pi, I for sure have a horizontal tangent, because at those values, the derivative is 0. dy dx is equal to 0. So that tells me that I for sure have a horizontal tangent at theta is equal to, negative 3 pi, negative pi, pi, and all those different values, just odd, multiples of pi. The way we're going to write this is theta is equal to 2n minus 1 pi for n an integer. So this 2n minus 1 part, what that means is that if you plug in any integer into that, and by integer I mean whole number, positive or negative, if you plug in any integer into that, that'll be a negative number. So you can try it out. If you plug in 2, you get 2 times 2, which is 4, minus 1 is 3. If you plug in 6, you're going to get 2 times 6 is 12, minus 1 is 11. So no matter what integer you plug in there, that's odd. So I can write, the odd integer multiples of pi like this. And so for theta is equal to 2n minus pi, 2n minus 1 times pi, I have a horizontal tangent line. And so let's figure out the points that happens at. So I have x of theta, again, so just recopying from above. X of theta is r times theta minus sine theta. Y of theta is r times 1 minus cosine theta. So if I plug in x of 2n minus 1 pi to get the x coordinates, this is going to be r times 2n minus 1 pi minus sine of 2n minus 1 pi. And so for any multiple of pi, sine is 0. So this is really just r times 2n minus 1 pi. So that's the x coordinate of all these horizontal tangents. I can do the same thing for the y coordinate, y of 2n minus 1 pi. This is going to be r times 1 minus cosine 2n minus 1 pi. And now this cosine of 2n minus 1 pi, these are numbers like cosine of, pi, 3 pi, 5 pi. Cosine of any of those is negative 1. So this is going to be r times 1 minus negative 1, which is 2r. So we have horizontal tangents at the point r times 2n minus 1 pi, comma 2r. And now let's figure out, so let's look back up here. So these values circled in blue, those are the places where dy d theta is equal to 0. All these other values, both dy d theta and dx d theta, are equal to 0. So I need to do a little bit of analysis. So let's go ahead and look at so we have dx d theta here, sorry, dy dx is equal to, so dy d theta, so what was that? That was r sine theta over r times 1 minus cosine theta. So let me go back up and check to make sure that I'm not writing anything down incorrectly. So r sine theta divided by r times 1 minus cosine theta, yeah. So this is sine theta over 1 minus cosine theta. So now let's look at the limit as theta approaches. So what we're going to do is we are going to do even multiples of pi. So we have the even multiples of pi. So if I go back up here, those are the lines that I've drawn that have these two things have in common. Those are the even multiples: 2 pi, 0 pi, 4 pi, 8 pi, whatever you like. So the even multiples of pi, we can write this as 2n pi for n an integer. Okay, so what we want to do is now we want to look at the limit as theta approaches 2n pi, let's say from the right, of dy dx, so sine theta over 1 minus cosine theta. I already know that both of these are going to 0. Sine of 2n pi is 0. Cosine of 2n pi is 1. So this is a 0 over 0. Let me do it in a different color. This is 0 over 0 indeterminate. So I use L'Hopital's. So by L'Hopital's, this is the limit as theta approaches 2n pi from the right. And I have cosine theta divided by 1 plus sine theta. Now when I plug this, when I look at this, look at what's happening here. As theta approaches, as theta approaches 2n pi, the top is going to, so cosine theta is going to 1. It's tending towards 1. Oh, sorry, I took the derivative wrong down there. Not paying attention. So this should be just sine theta down here. Yeah, so simple mistake. So I'm sure somebody will comment and before they see me correct this, but that's okay. Anyway, so this one's going to 1. This is going to 0 down here. If I have something going, so I have the numerator going to a number, and the denominator is going to 0 from the right, because we're a little more than 0. We're a little more than 2n pi. So this limit ends up being positive infinity. And you can do the same thing for 2n pi from the left, and you get the same result. So you have vertical tangents for theta is equal to 2n pi. Let's go ahead and figure out what the x and y coordinates are. So x of 2n pi, this is going to be r times 2n pi minus sine of 2n pi. And y of 2n pi is going to be r times 1 minus cosine of 2n pi. Let me make sure that I'm getting, yeah, no, these are all right. I'm worried about screwing up one of these derivatives. The derivative looks almost the same as the original equations. So I don't think I've screwed anything up so far. I think everything's fine. But anyway, so sine of 2n pi is 0, an even multiple of pi. So this is 2n pi times r up here. Cosine of 2n pi is 1, so this is going to be equal to 0. So the points where I have a vertical tangent line are going to be at 2n pi times r, comma 0. And that's the end of this problem. So this was a little more complicated, but you can look at the graph of the cycloid and you'll actually see this happening. The vertical tangent lines happen, periodically at 2n pi r, and the vertical tangent lines happen at the odd multiples of pi times r. So I'm going to stop this here, and now we're going to talk about integrals. Yeah, we'll move on to the a little more fun stuff.